Hello, my name is Jamie Tucker-Foltz, and I'm going to be presenting some new lower bounds on approximating the unique games optimization problem in fixed point logic with counting. There's also a 1-hour version of this talk that's geared towards a more general theoretical computer science audience, and you can find the link at the end of the slides. So I want to start by quickly reviewing the background on what fixed point logic with counting is, why it matters, and how you prove lower bounds for it. So as we all know, there are problems that are solvable in polynomial time, but not expressible in first order logic. So several extensions to first order logic have been proposed. First, there's least fixed point, where you add the power of writing inductive definitions. And then you can add on top of that numeric variables and counting quantifiers that assert that a certain number of elements of your universe satisfy a certain predicate. And this gives you fixed point logic with counting, FPC. And over ordered structures, this FPC doesn't really make sense because already LFP captures all of P. But over unordered structures, these are all distinct classes, and FPC is a very interesting fragment of P. Roughly speaking, definability over FPC means solvability by a polynomial time symmetric algorithm. In other words, an algorithm that isn't allowed to make any symmetry breaking choices. So for example, Gaussian elimination is a classic thing that FPC is not capable of doing, because in that algorithm, you have to repeatedly choose a pivot row and column. And you can't do that symmetrically. It's an arbitrary choice. So FPC captures what you can do without making arbitrary choices. It's one of those logics. And it includes a lot of powerful algorithmic techniques, such as linear and semi-definite programming. The standard approach to proving FPC lower bounds is via Ehrenfeucht-Frisé games, and where you assume towards a contradiction that there was some FPC sentence phi expressing your property P. And then you say, okay, then we can translate phi into infinitary counting logic CK for some K. And so what this is first order logic with counting quantifiers and infinite sentences, but still only K variables. And then to show the contradiction, you just have to construct for any such K two structures, AK and BK, where A has the property P, B does not have the property P, but A and B are CK equivalent. In other words, no sentence of CK can distinguish A from B. And to prove this last part, you use the characterization of CK equivalence in terms of a game between two players, spoiler and duplicator, called the K-Pebble bijective game. A and B are CK equivalent if and only if duplicator wins the K-Pebble bijective game played between A and B. And so all we have to do is show a winning strategy for duplicator. And how this normally goes is what's known as a CFI construction, named after Cypher and Immerman, who first came up with this technique, where you construct your two structures out of gadgets, where the two structures are identically the same except at one small place, which causes A to have the property and B to not have the property. And so even though they're non-isomorphic, duplicators should still be able to win the K-Pebble bijective game. And roughly their strategy is to make sure the pebbles are always placed in the same places within the same gadgets. And anytime that spoiler is close to exposing the difference between the two structures, duplicator will apply automorphisms between the structures to essentially move the inconsistency around the graph somewhere else, far away from the pebbles. This paper is extending this idea to the realm of inapproximability. And what that means is that to show a lower bound, it now no longer suffices for A to have some Boolean property and B to not have that Boolean property. But there's an optimization problem, and A should have a very high optimal value and B should have a very low optimal value. And what this means is that we can't have the two structures look the same except in one small place, because such structures will have almost the same optimal value for any reasonable optimization problem. In other words, the picture actually should look like this. The two structures have to be vastly different and only the same in some small patch of consistency where the pebbles are. And this isn't the first paper to face these challenges. There's one prior work by Atseris and Dewar in 2019. It's considered the 3 XOR problem, which is like 3 SAT, except you have XOR clauses instead of SAT clauses. And what they showed was a 1, 1/2 plus delta inapproximability gap. In other words, they constructed a sequence of 3 XOR instances, AK and BK, where in AK, all the clauses were satisfiable, and that's what this 1 corresponds to. But in BK, only slightly more than half of the clauses were satisfiable. And what this implies is a tight FPC inapproximability result for 3 XOR. From this initial gap construction, they use reductions to show an FPC inapproximability results for a handful of other problems. So the problem that this paper is concerned with is unique games. And unique games is a CSP, which means it has a set of variables, a domain that those variables take values in, and a set of constraints that are applied to those variables. And as always, the objective is to find an assignment of variables to values in your domain, satisfying a maximum number of constraints. And for unique games, there are restrictions on what kind of constraints can occur. They can only be between pairs of variables, And they have to be of the following form. If you have some constraint C between a pair of variables x1 and x2, the value of x1 uniquely determines the value of x2 that will satisfy C. And the main theorem is that for any delta greater than 0 and any positive integer L, we construct a sequence of unique games instances AK, BK on some fixed domain size such that the optimal value of the AKs are high, the optimal values of the BKs are low, and A and B are CK equivalent. And so how high and how low? Well, let me just plug in L equals 1. This is one of the most interesting specializations of this construction. And if you plug in L equals 1, what this means is that for any delta greater than 0, there exists some Q, domain size, such that no sentence of FPC distinguishes unique games instances on a domain size Q that have optimal value at least a half from those with optimal value at most 1/3 plus delta. In other words, this is a 1/2, 1/3 inapproximability gap. And what this means is that just as in classical complexity, if you show hardness of a gap problem, you get hardness of approximation. Well, here we have an unconditional result showing that there is no FPC sentence distinguishing these two cases in this gap problem, and it implies that there is no FPC definable algorithm giving an approximation ratio of better than 2/3, because the 2/3 is the ratio between the 1/2 and the 1/3 in the gap. And in fact, we can do even better than that, because if we send L equal to L to infinity, then what this means is that for any constant, there's no alpha approximation algorithm for any constant alpha definable as an FPC interpretation. Okay, so how do we define our AK and BK for this construction? Well, let's let K and L be given. Remember, L is just a parameter that affects the satisfiabilities of the two instances. So first we choose very large positive integers, R much bigger than M, much bigger than L. And then we pick some graph where every vertex has degree 2 to the L plus 1, and it has girth at least K plus 1 squared R. So the length of the small cycle is at least K plus 1 squared R. Then for every edge, we associate a random vector B of E in the vector space F2 to the M. In other words, the M-dimensional vector space over the two elements field, or binary strings of length M under XOR operation, bitwise XOR. And we also associate a random L-dimensional subspace of this vector space to each edge. And we call that Z of E. Then the crucial step here is we remove any bad edges. And what's a bad edge? A bad edge is an edge E such that there's some path starting at that edge of length R, where if I take all of the subspaces encountered along the edges in that path, that fails to span the vector space. Okay, these will cause trouble for duplicator. So we just remove all those edges. Okay, but all I've just defined is the squared graph and these vector spaces. Now I haven't told you what the two instances A and B are. So here's how they're defined. So A and B are going to be unique games instances where the variable set is the vertices of this graph H cross the vector space. Okay, so down below here, this is what a typical variable looks like. I've written the vertex index as a subscript and the vector index as a superscript. And the domain is the vector space F2M as well. So you have to assign variables values in F2M in this vector space. And then here are the constraints for any adjacent vertices and any two two vectors in this vector space, and any Z in the subspace between those two vertices that is associated to that edge. We add the following constraints. Here are the constraints we add in A, here are the constraints we add in B, and these are as equations in the vector space F2 to the M. And notice they only differ by this random vector, and this is what causes the B instance to be less satisfiable. And you can check that these are indeed unique games constraints, because if I fix the value for one of these variables, there is a unique value of the other variable that will satisfy this equation. And that's just by linear algebra. So here's an example of this construction where the underlying graph is K4 and M equals 2. Okay, so in other words, our vector space is F22. It's binary strings of length 2. And I'm notating this by putting the vector spaces along each edge as these set of vectors here. So for an example, how to read this diagram, what are the constraints involving these two variables, x1, 0, 0, and x2, 1, 1? Well, I look at the edge between the x1s and the x2s. It has 0, 0, and 0, 1 in the subspace, so I put that here, 0, 0, and 0, 1, and these are just the constraints by definition. And I've just simplified them here. Okay, so this is the full example here. And here, these two structures are going to be C3 equivalent. And so how do we show that? So let's say we're playing the 3-pebble bijective game. And at the beginning, duplicator will keep giving an identity bijection between the two structures until we get to a point where we have a pebble on one of the ends of this red edge where the two structures differ, because I have different subspaces here. Here I have 0, 0, 0, 1. Here I have 1, 0, 1, 1. If I give the identity bijection again, and then spoiler puts the pebbles down on this bottom left vertex, the x3 ones anywhere, because these subspaces are different, the constraints are going to be different, so duplicator will lose. So what does duplicator need to do? Well, we have to permute the variables within this little gadget here to ensure that we have consistency. And the permutation is going to be by sending, the bijection is going to be defined by sending x3a to the x3a plus b for some fixed vector b. Okay, that's always the form of duplicator strategy. And you can just check that by the definition of how this was all defined. If I want to have consistency between the two structures over the x1 and x3 variables between, so in other words, this edge and this edge, then b better be either 0, 0 or 1, 0. And if I want consistency across this bottom edge, then I want b to be either 1, 0 or 1, 1. So hey, it looks like we're in luck. If I choose b to be 1, 0, then both of these edges will be consistent. And so I'm putting in a 1, 0 here. And the general reason why this always works is linear algebra. This will boil down to solving a system of two equations over two unknowns in order to make this path of length 2 that goes from the x1s, the x3s, the x4s consistent between the two structures. And what this has really done here is, if I view these two structures with this permutation in mind, what I've essentially done is I've used this automorphism to shuffle the problem edge from the bottom to this edge over here. Now they look only inconsistent where there aren't any pebbles. So no matter where spoiler puts the pebble pair down, duplicator will not lose immediately. So for example, if they put the pebbles on x300, the corresponding one will go on x310 here, and you can check from the constraints that this looks consistent across both structures. And so just to show one more round, say spoiler picks up this top pair of pebbles. Well, now we need to worry about this middle guy. If spoiler puts them down on the x2 variables, then we could have a problem. So we need to permute these and do the same computation to make sure that we have consistency between this edge, and between this edge and this edge. Okay, and that's all spoiler duplicator has to do. And you can just play this game ad infinitum and check that indeed spoiler will never be able to win. So these two structures are C3 equivalent. And this despite having different optimal values. Duplicator's general strategy for the general construction is to maintain consistency between the two structures over a spanning tree between all the vertices in H that were pebbled. Okay, so this is a very small portion of the graph. Everything else might look completely different. And so this is a very weak invariant, but it's easy to preserve if spoiler, say, puts pebbles down on adjacent vertices. We're just growing this tree out by a little bit, changing the tree by small amounts by basically making neighbors in this graph consistent between the two structures. That's always possible to do, and it's easy. The only problem is when the minimal spanning tree between the pebbled vertices changes dramatically. And now here we might have situations where I have paths where both endpoints have fixed values in terms of the permutations that have been applied to those vertices. And now I worry that's not always possible to do, to choose permutations for these gadgets that make the structures consistent here. But here's where we use the fact that the graph had high girth. Whenever the tree changes like this, because it had high girth relative to R, you can show that such a path that needs to be made consistent has length at least R. And because we've removed all the bad edges, you can check that this enables duplicator to find intermediate values for all the vertices, making the structure consistent along these long paths. And this is kind of what we did in this previous example. Here, R was 2. So we wanted to make this green path consistent between the two structures, and we wanted to find an intermediate value for this middle vertex that made this path consistent. And for this instance, it just so happened that this is a good path and R equals 2, so it was possible. So just to recap, the main contribution to this paper is a new proof technique adapting the standard CFI constructions in the realm of inapproximability, where you have a weak invariant of the two structures only being similar over a very small region of the graph. And we use this to show some new lower bounds on approximating unique games in FPC. An outstanding open question is whether we can widen this gap. You may be familiar with a unique games conjecture in classical complexity theory. Well, it turns out there's an FPC version of this as well. And if we can make this gap instead of 1/2, 1/3, we want 1 minus epsilon and delta for arbitrarily small epsilon and delta, then analogs of all the things that are true, assuming the unique games conjecture in classical complexity, there are analogs in FPC as well that are very interesting. And if you want to hear more about that, I recommend seeing the longer version of this talk. Go into more detail about why this FPC unique games conjecture matters. Finally, I want to thank Anuj Dawar a lot for advising this project while I was at the University of Cambridge.